This tutorial is going to cover equilibrium topics that are discussed in Chapter 14 and somewhat compare and contrast them to reactions and topics discussed in Chapter 13 because there will be many differences here. First and foremost, of course, is discussed what equilibrium reactions are, which are bidirectional reactions. And in the last chapter, we were looking at unidirectional. And what we mean by that is that in an equilibrium reaction, we are looking at a double arrow present in the chemical equation. So it's a very easy way to spot an equilibrium equation, looking for the double arrow. And in the last chapter, of course, there was a single arrow because there was a start and a finish. And equilibrium, of course, means that the reaction can proceed in both the forward as well as the reverse directions, or is reversible. And looking forward in writing equilibrium rate expressions or rate constant expressions, we're actually going to be looking at both reactants as well as products, whereas in the past, in Chapter 13, we were more focused on only the reactants. Here we're focused on both reactants as well as products. And we aren't actually going to have such an arduous process to determining our K value, whereas we have to plot the rate versus time, and of course we got the rate from plotting the concentration to time and going through all that data just to get the K. We actually find K for the reactants and products simply by using the law of mass action here in Chapter 14. Of course, looking at this hypothetical equation, A plus B equals C plus D, where the capital letters, of course, represent your reactants and products, and the lowercase letters represent your coefficients. Again, what we're looking for is a double arrow, so that is equilibrium. And to write our K expression, according to the law of mass action, it is products, that's C and D, concentrations, that's what the brackets represent, each to the power of their coefficients, so capital C to the power of little c and capital D to the power of little d, all over your reactants, written in the same fashion. So products over reactants, products concentrations times one another over reactant concentrations times one another, and the exponents here are actually just your coefficients. So again, there is yet another difference here in equilibrium reactions, where your coefficients indeed do become your exponents. There is no need to look again at a data set and analyze it in order to determine the exponents or the orders of the reaction. The exponents simply are your coefficients. So here's some guidelines in writing your equilibrium constant expressions. Number one, of course, that the concentrations are always written in molarity units. That's what the bracket represents. So it's in molarity units. Sometimes if you're dealing with a gaseous phase of a reactant or product, the expression can still be written in terms of molarity, in which case you will see that concentration again in brackets. Sometimes you will see it as a P, which represents the concentration of that gas in pressure units of atmospheres, but that's only for gases. Everything else will always be in terms of molarity. The second thing, of course, is that we do look at reactant and product concentrations. However, the concentrations of pure substances, such as solids and liquids, okay, and solvents, do not appear in the equilibrium constant expressions. That means if you see a solid notation or a liquid notation, you will not include that reactant or product in the K expression. Only aqueous and gases should appear. The third is that the equilibrium constant is a dimensionless quality. Even though we have concentrations of molarity or concentration units in pressure units of atmospheres, we don't worry about what cancels what. K in this case will be a dimensionless or unitless quantity. And so there is no knowing what the unit for K is for this order or for that order. And of course that was a very big deal in Chapter 13. So again, another difference here. Number 4, in quoting a value for the equilibrium constant, again, you must specify a balanced equation so that we can, of course, see what the reactants and products are, and a temperature. Now, you may not actually use that information in the problem or in the calculation, but it's just proper or standard notation to include the equation as well as the temperature. Number 5, if a reaction is expressed as a sum of 2 or more reactions, meaning that there's a series of steps in that particular reaction, the equilibrium constant for the overall final equation is given by the product of all of its equilibrium constants. So if you have reaction 1, that'll have a K number 1. Reaction 2 will have K number 2. Reaction 3 will have K number 3. And then if you want to find out what the final total reaction is, you will also want to know what the K value for that overall reaction is. You would multiply the K1 value by the K2 value by the K3 value. And while this doesn't occur very often, it does occur in reactions with mechanisms or reactions that have multiple steps. Number 6, of course, again, notice here, as opposed to Chapter 13, that both the reactants and products are used in the calculation of K. Number 7, notice here again, as opposed to Chapter 13, that the coefficients are the orders of the reaction or the exponents. There is no need to look at a data set. And again, very easy to determine that when you are at equilibrium and when you're not is by looking at the double arrow notation, because the 2 directions will signify what an equilibrium is. And again, depending on what equilibrium reaction you're looking at is and what your reactants and products are, it's very relative. If we're going in the forward direction up here, then of course A and B are our reactants and C and D are our products. If we're going in the reverse direction, then C and D are our reactants and A and B are our products. So it's very important to make note of which direction you are operating under, the forward or the reverse. And that's why it's important to specify the balanced equation in the problem so the person reading it actually can make that determination. So we're missing here a double arrow, but we know that we're under equilibrium being in this chapter. Let's take a look at this example and writing the K for it. 2NO2 gas yields 2NO gas plus O2 gas. So again, the K would be products over reactant concentration. So NO concentration to the 2 power, because it has a 2 coefficient, times the other product, O2 concentration here, to the power of 1, because the coefficient here is 1, all over the reactant, which is NO2. There is a concentration of NO2, and it is to the power of 2, because there's a coefficient of 2. So again, all you have to do is products over reactants. Given that these were all gases, we could write the K expression in terms of concentration, which is what these brackets mean, or we could have just said, for example, this is the P of NO squared, the P of O2 to the 1 power, divided by the P or pressure of NO2 squared. So again, you could use either unit, but it's always products over reactants, and the coefficients will still be your exponents. So it really doesn't make a difference. It's just a matter of whether you're solving for pressure or molarity units. Here's another example. Calcium carbonate, which is a solid, will decompose to form calcium oxide as a solid and carbon dioxide gas. So in this case, what are we going to do when we write the K expression? We're going to assume that solids and liquids as pure substances are constant values of 1, meaning that they are not present in the expression. So products over reactants would be carbon dioxide gas with a 1 coefficient would be carbon dioxide as the product to the power of 1, which is its coefficient, times the other, which would be calcium oxide, which we would put as 1 just as a placeholder because solids are not present, all over the reactant. And the reactant, of course, is a solid, so again we'll put a placeholder of 1 because it won't affect the K expression. CO2 times 1 divided by 1, of course, is CO2. You could have just even disregarded the ones if you did not want them as a placeholder, if you already knew that the solids were constant values and therefore not present in the expression, and you would have attained the final answer of K is equal to simply the concentration of CO2 to the 1 power. And that's simply all we would have done in that case. Again, only solids and liquids are considered to be the pure solvents or substances, and they are not to be present in the final K expression.